This is a relatively short revision video on Mathematics Core 2 from Edexcel AS level. Hope it helps. The first thing we're going to cover is algebra and functions, which covers stuff like the remainder theorem and long division and stuff like that. F of x is a function, and if f of a is equal to 0, it means that x minus a is a factor of f of x. And there's an example on the next slide which will help to explain this a bit better, hopefully. So we have our function f of x, which is 12x minus 48. And f of 4, we've been told, is equal to 0. So we know, because we know the rule, that f of a is 0, x minus a is a factor. So we know that x minus 4 is a factor of f of x. And we can prove this by taking it out, and we've got 12x minus 4, so we've just shown it's a factor. You can divide it by x minus 4 and be left with an integer. If f of x is a function, f of b over a is equal to 0, we know that ax minus b is a factor of f of x. So it's basically the same as the previous one, but a tiny bit more complicated, and we'll have an example on the next slide. So our function is 12x minus 8, and we've been told that f of 2 over 3 is equal to 0, so when x is 2 over 3, the whole function is equal to 0. And because we know that if f of b over a is equal to 0, ax minus b is a factor, we know that here ax minus b, so the a is 3 and the 2 is your b, so 3x minus 2 is a factor, and we can show that because we can take it out and be left with 4, and then in the bracket it's 3x minus 2, and if you multiply it out you'll get 12x minus 8, which is the original function. If f of x is a function, f of x divided by ax minus b gives the remainder f of b over a. At the moment I'm basically giving you a load of rules, and they're very easy to learn and to know. It's about applying them that's the difficult part, and I can't show you how to apply them on a video, and it took me a long time to learn how to apply them. I hated this chapter, but once you learn how to apply them in questions, they're really easy marks. Here we're actually going to apply some of the stuff we've learnt. So we know that f of x is 2x squared minus bx minus c, and we need to find b and c. So we know that 2x plus 4 and x minus 5 are factors, and because of the rules we've learnt, so 2x plus 4 means that f of 4 over minus 2 is equal to 0, and that means that when the function of minus 2 is equal to 0, so we can sub all our stuff in and we get 8 plus 2b minus c equals 0. And then our other one, x minus 5, we know that 5, when we use it, function of 5, it's equal to 0. So 50, when we've subbed it in, minus 5b minus c equals 0. Then it's just a case of applying basic GCSE simultaneous equation knowledge, and we'll have our simultaneous equations, which are 8 plus 2b minus c equals 0 and 50 minus 5b minus c equals 0. And I think what we're going to do is take one of them away from the other. We're going to take the blue one away from the red one, and we'll be left with 42 minus 7b equals 0. So for that we can take the 7b over, so 42 equals 7b, divide both sides by 7, and we get that b equals 6. Sub that into one of the original equations, so we'll go for the blue one. 8 plus 2 times 6 is 8 plus 12, which is 20. 20 minus c equals 0. Take the c over, c equals 20, and that's your answers. I chose to do a relatively simple function so we can prove that this is correct, show you it's right. Maybe it'll make you feel a bit calmer, happier in the head. If we multiply our two factors together, we get 2x squared plus 4x minus 10x, which is minus 6x, minus 20. And then we've got b is 6 and c is 20. There are quite a lot of different types of simultaneous equation questions that you'll come across. They'll probably be worth quite a few marks, so it's good to get some practice, and this is just an example of one. Something else that you might come across in the algebra and functions chapter section of your paper is the division of polynomials. You might have learnt this as long division. I learnt it as the grid method. I mean, I can do long division, but I've decided not to put it in this video because it's quite a long process to put out, and I think the grid method is much easier and much better. And I've joined my maths teacher as an advocate for the grid method. I mean, for a long time I hated this method with a passion, but then suddenly it clicked and I just loved it. So we're going to do a quick example here, and I'll just show you how it works as we go along. So say we're doing x cubed plus x squared plus x plus 1 divided by x plus 1. First we'll draw a grid, and we know it's got 2 rows because there's the x and there's the 1, so there's just 2 in the thing we're dividing by, and we'll put those along the side. We know that the first term that's going to be in our grid is x cubed, because that's the first term in the original polynomial. So we put our x cubed into the grid, as you can see in step 2. To get our x cubed, we have to multiply our x by something. In our head we're thinking, oh, what is that? And we know it's x squared. So as you can see in step 3, we're going to put x squared at the top of our grid above the first column. We're then going to look down our grid and do a multiplication, and we know that we're multiplying x squared by 1, which gives us x squared. Once our first column's completed, we have to see what else we need. So say we wanted to have 2x squared, we'd put a plus x instead of where we've got the plus 1, but we don't. We only want 1x squared and we've already got it, so we're moving on to the next lowest power, which is x, just x to the 1. So we're going to multiply x by 1 to get plus x, and then multiply along the bottom plus 1. So now we've got x cubed, x squared, x and 1, and that is our entire polynomial. So we've shown that x cubed plus x squared plus x plus 1 divided by x plus 1 equals x squared plus 1. Again, I've chosen relatively easy numbers, so we can just multiply it out. So if we multiply x squared plus 1 by x plus 1, we should get our original polynomial. So that is x cubed plus x squared plus x plus 1, when we expand our brackets, which is our original polynomial. So we've shown that the grid method works. Well, at least we've shown it works in this situation, but so you don't worry, it works for all situations. You can use it to find the remainder, but I prefer to use long division to find the remainder. And hopefully you can already do long division because it's quite straightforward. It's effort, but quite easy. If you can't do it, then contact me, tell me, and I will explain it for you. After that quite difficult chapter, we're moving on to the sine and cosine rules, which are quite nice, straightforward things. This is a diagram of a triangle, just so we're all on the same page when I'm talking about A's, B's and C's and stuff like that. I've put it on all the other slides as well, just so you can see it when you're looking at the equations. So for a typical triangle, our capital letters are our angles, and they are directly opposite the small lowercase letters, which correspond with the sides, and that's the length of the sides and the size of the angles. You'll use the sine rule when you've got 2 side lengths and 1 corresponding angle and you're looking for another corresponding angle. So say you've got A and B and the angle's B, but you want the angle A, that's when you use the sine rule. Or you'll use it when you've got 2 angles and 1 corresponding side. The sine rule is A over sine A equals B over sine B equals C over sine C, though in reality you're only ever going to use 2 of those at once. So for example, A over sine A equals C over sine C. That'll probably be the most you're going to use. So say you want to find side B and you've got side A length and the angles A and B, you'll do length A over the angle A signed multiplied by sine of angle B, and that will give you length B. A very common rearrangement of this would be to flip it all over. So you'd have sine A over A equals sine B over B equals sine C over C. And that's exactly the same, it's still the same formula, it's just easier to find your angles this way. So say you wanted to find angle B and you've got angle A, and side B, you'd do sine A over A multiplied by B, all in brackets, would give you sine B. And then you do sine to the minus 1 of all that big stuff in brackets, and that'll give you B. Sine to the minus 1 is that button on the calculator. You might have been taught it being called inverse of sine or arc sine. You will use the cosine rule when you've got all 3 side lengths and you want to find an angle, or when you've got 2 side lengths, 1 angle, and you want to find the other side length. Incidentally, you get the cosine rule given to you in your formula booklet. This is the only trigonometric rule that you get from this chapter for Core 2, but you do get it in the first form, you don't get it in the second form. The form you get it in is a squared equals b squared plus c squared minus 2bc brackets cos a, so 2bc multiplied by cos a. The form that one is used for, it's used to find the side length when you've got the corresponding angle of the side length and 2 other sides. If you've got 3 sides and you want to find the angle, you'll rearrange it to get a, which is the angle, equals cos to the minus 1 of brackets b squared plus c squared minus a squared all over 2bc, close brackets. There's no need to learn that really because it's quite a simple rearrangement of the formula. It's just nice to see it so you've got an idea of what it looks like. You'll use the area of a triangle formula when you've got two side lengths and the angle in between them. And the area is half AB sine C. There's probably some very simple proof of this. I'm pretty sure I've seen the proof of this quite a few times, but you don't need to know the proof, so I'm not going to go through it with you. And I don't know it anyway, so hopefully that's alright. Logs. The word is enough to strike terror into the heart of any AS math student, but they can be conquered. I remember my first log homework, I spent 3 hours doing like 10 questions. They just took forever. And then suddenly logs clicked and I could finally do them, and that was just the happiest thing that ever happened to me. To get logs and to be able to do questions on them really easily, all you have to do is know your log rules and just practice loads of questions, and that's all you're ever going to need is your log rules. They're not trying to make it hard. The questions they give you in the exam are usually quite easy, so just learn your log rules and you'll be fine. This is the basics of logs. If a to the x equals n, log a of the n equals x. And the way I remember this is that the first one stays the same, so in both cases your a is in the same place as at the front, and then the other two swap places. And we've got an example on the right, so if 4 to the 2 is 16, log 4 of 16 equals 2, and you can check that on your calculator and you'll show it's right, and it's right for all numbers, because that's the rules of logs. This is probably the most important thing to learn. Just make sure you know it and you understand this, because if you don't understand this, understanding the rest of all the log stuff is going to be very difficult, so stop it now and learn this if you don't know it already. This is some stuff that you need to know for logs. Log a to the 1 is always 0, and log a to the a is always 1. So, for example, log 3 to the 1 is 0, log 3 to the 3 is 1, log 4 to the 1 is 0, log 4 to the 4 is 1. And then log 10a is the same as log a. And when you're in an exam on your calculator, the only one that you're allowed to type in is log a, so you shouldn't have any base, it should be log a, and we'll come to the base rearrangement formula later, so that you can always put log a into the calculator, because although you have got the button there, if you just do that and you put the answer down like that, they won't give you quite a few marks, so make sure you get all the marks and don't make that mistake. Though that button is a good check to see what you're doing and see if it's right. If you have log a of x to the power of k, that's exactly the same as moving the k to the front and getting k multiplied by log a to the x. Again, this rule is pretty useless by itself, but once you've got all the other rules and you're faced with a question, you need to have the full set of armour to be able to charge into battle and get a good mark. Yay, that was rubbish. Now here are your exciting log rules, and if you look at the first two, they're quite similar, so as long as you remember one of them, hopefully you'll be able to remember both. So log a x by y equals log a to the x plus log a to the y. And then log a to the x divided by y is the same as log a to the x minus log a to the y. So if you look at them, they're both quite similar. One's just multiply and then plus, and one's divide and minus. So the positive ones go together. I always think of multiplying and adding as positive, because they're quite happy things to do, whereas taking away and dividing, you're cutting something down, it's quite bad, so I put those two together. You don't really need to understand why these rules work, you just need to understand that they do work and be able to apply them in a question. The final rule is log a of 1 over y equals minus log a of y. I've never had to use that in a question, and in fact I didn't know that until I was typing it on here, but apparently that is the case, so make sure you know that, and I'll make sure I know it too. Here are the change of base formulae. And the first one you get given in the formula booklet, the second one I'm afraid not, but I've never used the second one. The first one is like my life, it's just the most exciting thing to do. You've got log a to the x, so say you've got log 3 to the 4, obviously you're not allowed to type that into your calculator, so you want log 10 to the 4, so you'll do log 10 to the 4 over log 10 to the 3. So your b value is the value that you want. The b value will pretty much always be 10. The a value is the original value, and the x is just the one you're doing it to. And from this we can derive the formula log a to the b equals 1 over log b to the a. Not so much with this log formula because it gets given to you, but with the others I always find it useful if I'm not 100% sure that I've got the formula right. I use some random figures and just check on my calculator that both sides of my formula that I believe to be true are the same, and if they're not, I know I've got it wrong. So that's just a test I use. I mean, you've been given a calculator, you've got quite a lot of time for this exam, you may as well use it. Time for coordinate geometry in the xy plane, which is basically some basic geometry and then circles. Fun, 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 you lucky people. The midpoint of x1, y1 and x2, y2 is x1 plus x2 over 2, y1 plus y2 over 2. I mean, if you look at it, you'll be able to see why. If you plot them down, it all makes sense. It's very basic, and hopefully you already knew that and you didn't need me to tell you it. This one is a bit more complicated because it involves the use of Pythagoras, and it's the distance between x1, y1 and x2, y2. To find the distance, you do the square root of x2 minus x1 plus y2 minus y1, and I've shown you y at the bottom. So we've got our 2 points, which are the two ends of the triangle, and they are x1, y1 and x2, y2. And we've got the x length, which is x2 minus x1, and the y length, which is y2 minus y1. And because we know Pythagoras, c squared equals a squared plus b squared, we can just apply this now with all the lengths that we know, and we get that c squared equals x2 minus x1 plus y2 minus y1. So we know that c, the hypotenuse, the diagonal, that length there, the length between x1, y1 and x2, y2 is the square root of x2 minus x1 plus y2 minus y1. Remember, it's all under the square root. And if you need to, I always draw this triangle when I'm working out the length. I don't know why, because I know the formula, but I always like just to see it, so I'm completely happy, and I'll write all the lengths along the sides. To see where two lines, circles, curves, anything, whatever, touch, you've got to make their equations equal, because you know when they touch, they're going to have the same y value and the same x value. So you choose one of y or x, and you put them equal to each other, and that gets rid of one of those values. I always go for y, but if it's easier to do x, go for x. So y equals 4x plus 12 meets y equals ax plus 4. So, oh god, got a bit of a cough here today. I think I sounded a bit like a toad at the end of that. Anyway, so we've got our two lines, and we know when they meet, the y value is the same. So y equals y, and 4x plus 12 equals 8x plus 4. And then if we rearrange that, we get that x equals 2. If we sub x equals 2 into one of the equations, for example the first one, we've got y equals 4 times 2, which is 8, plus 12, which is 20. So we know that they meet when y is 20 and x is 2. So they cross at 220. Wish I put it so that the x value is 4 now, so it'll be 420 for the general banter. What's that I smell? Whiffy banter? I actually love bad education. I don't watch much TV, but bad education, that's my thing. Moving on now to the equation of a circle which has centre AB and radius R. They'll probably get you to work out the centre and the radius yourself using the methods we've just used. So the midpoint will help you find the centre, and you'll get the diameter by doing the length between 2 points, distance between 2 points. Cut that in half, you get the radius. And we know that the equation of a circle is r squared equals x minus a squared plus y minus b squared. It's really important to get the signs right within the bracket. So say the centre of the circle was minus 2, 4, you'd have x plus 2 squared plus y minus 4 squared. Just make sure you get the signs right. I'm not sure when you're ever going to use this, but it's a nice circle fact if that's the kind of thing you're into. A chord is a line that joins 2 points in a circle, and a perpendicular from the centre of a circle bisects a chord, as you can see on that pretty diagram there. That means that the two sections of the chord on either side of the perpendicular, a perpendicular is a line that is at right angles to the chord, they're equal in length. So the two red bits, they may not look equal, but they are equal. An angle in a semicircle is always a right angle. Very nice to know. Again, I've never used it in an exam, but it might come up. I could do the proof for this if you wanted me to, but I think I've already done it in another video. If you just look circle theorems, you don't need to know the proof. It's just if anyone's really interested in maths, if that's the kind of person you are, then you can go watch that video and find out all about proving that the angle in a semicircle is a right angle. Incidentally, for anyone interested, the angle at the circumference is always half of the angle at the centre. Now this is one that comes up quite a lot. A tangent meets a circle at one point only, so it's basically a line that hits the circle once, and the angle between a tangent and a radius is always 90 degrees. With this one, quite often you have to draw two tangents on, and they'll meet at a point, and then use Pythagoras to work out certain lengths and distances and stuff. That's how I've seen it used in the past. If you want practice of that, just do past papers. I know that the 2013 Core 2 past paper had a question that you had to use Pythagoras and tangents, so if you want to use it and do some practice, then go for it. Now we're moving on now to binomial expansion. Laughing at my own joke here. There's a gnome, obviously. I don't take art, I've never been able to do art, so you probably can't tell that's a gnome, but that is my gnome because I'm hilarious making jokes today. I'm sorry, I was just a bit bored. I did all this morning and I got to halfway through the video now, if anyone's interested. Got halfway through, I was like, right, time to have some banter. So there's your gnome for the general bants. We're going to look at the number of ways of choosing R items from a group of N items. And if you go on your calculator and you go to it from the equal sign, if you've got a Casio calculator, which I'm guessing quite a few of you will do, you'll find the button that does this. So you'll have your number of items, original items. So for the example I'm going to show you, it'll be 3. Then you'll push the shift button and the NCR button, and you'll get 3, choose, and then R, which is how many items you want to choose. So say it was 0, you'll have one way of choosing 0 items, which is not to choose any of them. So say we've got our 3 boxes here. If we don't want to choose any items, there's just one way of doing that. If we're choosing 1, there'll be 3 ways of doing that. If you type in your calculator, you'll have 3C1. 3 choose 1, there's 3 ways of doing it. You can either choose the red, the blue, or the green. You'll have 3C2. There's also 3 ways of doing that, because you can choose the red and the blue, the red and the green, or the blue and the green, and that's the only 3 combinations of choosing 2 items. And then if you want to do 3 choose 3, there's only one way of doing that, and that's to choose all 3 items. So that's just a quick introduction to binomial expansion, how to choose things, and that's just the basics you need for the next slide, which is how to actually expand everything. Moving on to binomial expansion itself, we've got a sassy ass gnome down there with its cool hair, looks a bit bold. You want to be as cool as that gnome, that's not a lie. So say we're expanding a plus bx brackets to the power of n, so a plus bx times a plus bx times a plus bx however many times, n times. Well, they'll always tell you to do it in ascending powers of x. So your first one will have no powers of x, so you'll do nc0 times a to the n times b to the 0, and you'll get a number from that when you type it into your calculator, and that's the number you write down straight away. Then for your x, you'll do nc1 times a to the n minus 1 times b to the 1, and you'll get that number. You'll write the number down you get from that calculation, and then you'll put an x. Then you'll do nc2 times a to the n minus 2 times b to the 2, and that's your number of x squared. And you'll keep going for x cubed, x4, all the way up to x to the n, and you'll have however many x to the n's. Something really important to remember here, because I did a past paper on this a few days ago, forgot it, you always start with NC0 and you always go up from there, because I just started on NC1 by mistake. I forgot about the 0 altogether. Remember, on your first one you'll have your 2 zeros. Your C and your B will always have the 0, or the 1 or the 2 will have the same. Then your middle one will have n minus the 0, the 1, the 2, the 3, whatever. Usually on questions like this it will tell you only do the first 3 terms, the first 4 terms. So yeah. Remember, if it asks you to put in order, make sure you get your signs right. So for example, if it was a minus bx to the n, you'll have alternate positive and negative numbers of x squareds, or x cubed, or x4s, or whatever. Moving on now to radian measure, and when I first came across these I hated them with a passion. Now I'm still a bit iffy with them, but we get along sort of alright, and I can smell dinner. I'm really excited. Sorry, you're here to learn about radians, not my dinner. Now, a radian is 180 over pi, and so pi radians is pi times 180 over pi, which is, if we count top and bottom by pi, divide top and bottom by pi, we'll be left with 180, so pi radians is 180. So say AB, the arc AB, has the same as the length r, and r is the radius. We know that the angle between A and B, theta, is 1 radian. Obviously that theta there isn't actually theta. I looked so hard to find theta, I couldn't find it, so we're using that weird symbol from now on. Here are some really important things that you need to know. They come up so much. Arc length is L, which is r theta. So that length there between A and B is equal to the radius times theta. The sector area, which is the whole area there, is sort of like a shape of a slice of pizza. That is half r squared times theta. Just learn these, write them down, scribble them everywhere, make sure you know them. I remember when I went into my exam, first thing I wrote down was that, because I always remember formulae and just write them down straight away. Obviously once the time started I don't flick it open and start writing before it started, but as soon as time starts I write down a few formulae. It's always these radian ones and the one on the next slide. This little formula here gives you the segment area, which is the green bit, and it's half r squared theta minus sine theta with your theta and the sine theta in brackets. So essentially you're doing the area of the sector, which is half r squared theta, minus the area of the triangle, which is half r squared sine theta. And we got that triangle area through the triangle formula for area, from earlier on, the area of a triangle formula, the half AB sine C. Because if you look at it, that's what it is. So remember, if you're in the exam, you're suddenly panicking, you're thinking, oh my god, I've forgotten the formula, look at it and split it up and see if you can work it out, derive it yourself. Like, I've had to derive quite a few formulae in exams myself because I've just forgotten them, and it's not very nice and it's effort, but it's better than just leaving the question blank. Moving on now to geometric sequences and series, which are almost as exciting as arithmetic ones. A geometric sequence follows the form A, AR, AR squared, AR cubed, where A is the first term and R is the common ratio, which is the amount you're multiplying each term by to get the next. You might be given two of the terms and be asked to find the common ratio. So say you were given AR and AR cubed, you'd divide your AR cubed by your AR and you'd be left with R squared, and you'd square root that to get R. I mean, obviously you'd have numbers in there, but as long as you did it that way, you'd still get the same answer. Just substitute your numbers for your new numbers, if that makes any sense whatsoever, which I don't think it does. The nth term of a geometric sequence is AR n minus 1, because you've got your first term multiplied by r to the n minus 1, and it's to the n minus 1 because your first term hasn't been multiplied by r yet, it's just a. Obviously your geometric series looks the same, it's got a first term common ratio, it's just a bit different because it's got plus signs in rather than commas, so a plus ar squared plus ar cubed ... and forever on. Quite often you'll be asked to find the sum to a certain amount or the sum to infinity of a sequence. The sum to a certain amount, say n, is a, 1 minus r to the n over 1 minus r, which is the same as a, r to the n minus 1 over r minus 1. Obviously you'll sub in your first term, your common ratio, your number of terms, and I think you get that one in the formula booklet. I just checked and you do, and you also get the sum to infinity of a series, which is a over 1 minus r. Quite often you'll be asked to find the difference between the sum to infinity and the sum to a certain amount, say 50. So you work them both out and then you take one from the other to get the difference. Your common ratio could be a whole variety of numbers. If it's a negative number, your terms will vary between positive and negative, alternatively. If your common ratio is between 0 and 1, your terms will get smaller and smaller and smaller in size, and if it's greater than 1 they will increase in size. I think the example quite likes to chuck in the ones that make it smaller and smaller and smaller, because I've never had one where it gets bigger, but I always get them where they get smaller. But don't bank on anything. Differentiation has got a lot more exciting since we did it in Core 1. On a graph you'll get a minimum point, which is the lowest y value on the whole graph, a maximum point, which is the highest y value on the whole graph, and a point of inflection. You also get local maximums and minimums. A point of inflection occurs, for here it's when it goes up and then it just slows down and then it goes up again, and you'll always have a gradient of 0 for a point of inflection in Core 2. So how do you find the coordinates of a stationary point, I hear you ask? Well, you solve f of x differentiated equals 0, so you'll differentiate it, you set it equal to 0, solve it to find your value of x, or values of x if you get a quadratic, and you will sub them into y equals f of x, and you'll gain your value of y. So you'll have your values of y and your values of x, and then you can find out the type of stationary point by doing the stuff which I hope is on the next slide. Okay, so finding the type isn't on this slide, hopefully it's on the next slide. This slide is about proving that a point is a stationary point. To prove it's a stationary point, if your differentiated f of x, when you've subbed in your value of x, has a value of 0, that's a stationary point. Now here's that special slide about the type of stationary point. If you differentiate f of x, and then you'll get f flip x, and you sub in your given value of x, so you've been given a value of x of your stationary point, or you found it yourself, you sub it into double differentiated f of x. If your value is greater than 0, then it's a minimum point, so it's really good to remember that greater is minimum, smaller is maximum. I know it makes no sense, but but obviously it makes sense, but in your mind it doesn't make sense because it didn't make sense in mine. But if it's greater, then it's the minimum. If it's less, then it's the maximum. If you get exactly 0 into double differentiated f of x, triple differentiate f of x, and if it doesn't equal 0, then you've got a point of inflection. I've never come across that before, but it's just nice to know. It might come up. There you are. For your range of a function, you'll put your minimum point, your value of y in, your f of x, and then the maximum point, the value of y. Obviously, for quadratics and stuff, you'll only have a minimum point or a maximum point, so you just get rid of the other one. Again, this doesn't come up much, but if it does, it's worth the mark, so you may as well get the mark. Graphs of trigonometric functions, i.e. hell. This is a cast diagram. You may or may not have been taught it. If you have, then I feel really sorry for you, because we were taught it and I absolutely hate it. It basically tells you which values are positive and which are negative. It goes round anti-clockwise. For the sake of ease, we're going to start in the top right hand corner where it says A, and the A stands for all, and all angles have a positive sine, cos, tan in that area. So between 0 and 90 degrees they're all positive. So say you type into your calculator sine of 35, it's positive, cos of 35, it's positive, tan of 52, that'll be positive. They're all positive in there. Whereas if you flip over to the next one, which says S, it means only sine is positive. So if you have sine of 98, that'll be positive, but tan of 98, I'm afraid to say, is negative, and for those of you who are interested, it's negative 7.115. Going down to T, T is for tan, and tan is the only one that will give you a positive answer in that one. And then C is for cos, and cos is the only one that will give you a positive answer in that one, so between 270 and 360. It's a nice diagram to know, but I don't know why I'd want to know it, because I never use it anymore. I used to love it, but now I hate it. I think it's if you use it instead of your graph shape, and you'll know how many values you should have, but I think it's just really confusing. But if you were going to use it, for example, you were to find all the values of x in the range 0 to 180, where x equals sine to the minus 1 of half, for example, you type that into your calculator and you'll get that x is 30, and if you look at that and you draw 30 on, between 0 and 180 there is another value of x that will work, because if you flip it over, because you know that 180 minus your original x will give you the same answer, you know it's positive, and it is 150. I'm not sure why I'd ever want that, but apparently that's what you have to do. This is a quick diagram which explains why each of your values are positive or negative. Because if you look at sine theta is y over r will still be positive in the second quadrant, but if you flip it so that it's in the third or fourth quadrant, the y will be down, which means the y value will be negative, so the whole thing will be negative. We could go through that for all of them, but I'm sure you can work them out for yourself, and I don't want to waste the time for people that weren't taught this method and were actually taught to use the graphs, which I prefer quite a lot. This is one period of this sine graph. The period's 360 degrees, so sine of theta is the same as sine of theta plus 360. If you use this graph, you can see that there'll be two values of sine theta that equal x for each 360 period. And because the graph is symmetrical about every 90, like plus 90, minus 90, it's symmetrical about that, you can tell what the other value is. We know that sine of 45 gives us root 2 over 2 on our y-axis, and to work out what other value of theta gives us root 2 over 2, we can use symmetry of the graph. So if you look at the graph and plug 45 in, it gives you the same height as if you do 180 minus 45, which is 135. So sine of 45 and sine of 135 both give you the same value of x, which is root 2 over 2. So it's really important to know that for sine, for every 360 degree period, you'll have two values of theta which give you x. So make sure when you're solving an equation you give both of them. I'll give a better idea of how to make sure you've got these values in a few slides after we've looked at all the other graphs. Apologies for my terrible drawing here, but this is what a 360-degree period of a cosine graph looks like. It is essentially the sine graph, it's just been shifted 90 degrees to the left or right, depending on how you look at life. Because the period is still 360 degrees, cos of theta is equal to cos of theta plus 360. Whilst for the sine graph, to get x, you could do sine of theta or sine of 180 minus theta. For the cosine graph, you have to do cos of theta or cos of 360 minus theta. So it's just important to remember that this one is 360 and for sine it is 180. And you can work that out by drawing the graph out yourself. Just make sure you remember that it crosses the y-axis at 1 when it's up 1 and the x-axis at negative 90 and positive 90, and then you can just draw it out going sideways. It's not very well drawn because I'm not an artist, sorry. This is a tan graph, and there are so many funny jokes you can make about tan lines, so look on the internet for them because I really can't bother to tell them right now. Tan graph has a period of 180 degrees. It's quite a sassy graph, quite a nice curve it's got there. It has asymptotes every 180 degrees, so at negative 90, positive 90, and then every 180 degrees each direction after that. Because its period is 180 degrees, tan theta equals tan theta plus 180, and you can just shift it, add 180, take 180, and it'll give you exactly the same value of x. So tan theta minus 180 is exactly the same as tan theta. As long as you remember the basic shape of the graph and that it crosses at the origin, you should be able to just keep drawing the graph if you need to. If you have the graphs in front of you for this one, it'll be easier for you to see why each of these is the case. But it's important to remember that sine of negative theta gives negative sine theta and tan of negative theta gives negative tan theta, whilst cos of negative theta is exactly the same as cos of theta, and if you look at the graphs you'll see why that is. For these, if you can't remember it, it's very simple. Just get your calculator in the exam and try, for example, cos of 50, which will give you 0.64, and then do cos of negative 50 and you'll also get 0.64. And any number, you can use any number you like, it just makes you feel a bit happier because you've checked it and you've checked that each of these is the case. So if you can't remember them, that's what I do at least. I mean, these don't come up very much, it's just a nice fact that you can know. Some more things that are quite interesting to know are that sine 90 minus theta is the same as cos theta, whilst cos 90 minus theta is sine theta, and this is simply because the graph has been shifted left and right, or left or right, whichever one you want, by 90 degrees. Trigonometric identities and simple equations. I don't know why they call it simple, because it really isn't simple. I do further maths, and there's the legendary maths breakdown, and everyone has a breakdown at some point in their further maths career, and I had mine over these supposedly simple equations. I just couldn't get to grips with them. But, I mean, I can do them now, just about. I think it was coming on to core 3 and seeing the trig equations there, they just, hated them so much. But if you just keep working at the identities and equations, eventually it will just click, and life will be fabulous. Some really basic trigonometric stuff you need to know is that tan theta is equal to sine theta over cos theta. Just learn that, have it ingrained in your brain. Learn it, love it, live it. I think that's my school motto. Jokes. Again, if you ever want to check that this is the case, just try it on your calculator. If you think, now is it sine theta over cos theta or cos theta over sine theta, just try some numbers into your calculator and you'll be able to work out which way around it is quite soon. Again, sine squared theta plus cos squared theta equals 1. This identity is really important, so make sure you know it thoroughly. And they'll always get you to do a bit of division, so they might give you a different equation or identity and get you to show why it's true, and you've just got to divide a bit until you get sine squared theta plus cos squared theta equals 1. Or you might have to sub stuff in, square numbers. Remember that sine squared theta is the same as sine theta squared. I don't think they'll ever get you to prove it. If you want to prove it, you just have to use Pythagoras, and you'll be able to work it all out from there. So in core 2, if you ever come across identities or equations, stuff you have to solve, it'll be those two. They're the only two formulas that you have to use in this. You might have to divide both sides by something, add something to both sides, but those two formulae are essentially the only thing you have to use. It gets a lot harder in core 3 when there are like 50,000 different identities and equations you have to know, but for core 2, as long as you know these and you can apply them, you should be absolutely fine. Just do loads of practice. This is all the stuff we went through in the previous section, but it's so important. So if you haven't got it written down somewhere, then stop now, take a photo of the screen, write it all down or something like that. Make sure you've got this written down, because this is the one that will give you all of the solutions, because you'll get one solution when you solve your problem, but this makes sure you've got all of the solutions in the given range. So say it asked for the solutions to a problem in the range 0 to 180 degrees, and you've got that sine of 45 gives you x. Make sure you also put that sine of 135 gives you x too. And obviously you'll have to write down whatever values you get, you know, theta equals this, theta equals this. I tend to work them all out, then write them at the bottom in a list in like numerical order going upwards. It just helps the examiner, because that's how it will be written down on his exam paper. And if you put the examiner in a good mood, it's generally a good thing. I mean, we've been through all of these already, so there's no point in me really going through them again now and explaining them. Just make sure you know them, love them, live them. They're the most important thing. Well, they're not, but I think they're really important. I mean, it took me a while to realise how important they were, but as soon as I did, I just learned them straight away. I was like, these are life. Because the sine and cos graph have a period of 360, any value of x you get, you can just add 360 to it, and it'll give you exactly the same value of k. Whereas for tan, it's a period of 180, so just add 180, take 180, it'll give you the same k value. This is the final chapter clip bit. It's on integration, and hopefully I'm a bit more awake for it this time than I was in the core 1 video. I've just been to the gym, so I'm proper pumped. That might also have been the most embarrassing thing I've ever said on a video. Integration, if you can't remember, if you add 1 to the power and divide by the new power. Integration tells you the area under a curve between defined limits. I think it's called the definite integral or something, and I'll explain all of that on the next slide. So say you've got a curve and you want to find the area under it between the values x equals 4 and x equals 6. You'll write that out and you'll put your a as the 4 and the b as the 6. The a is always the 1 on the left and the b on the right. You'll sub in your f of x and then you will integrate it. So you'll now have your integrated f of x and your value of a and your value of b. You're going to sub in your value of b and then you'll write down what that gives you. And then you're going to sub in your value of a into the integrated function and you'll write down what that gives you. And if you take a away from b, you'll get the total area under the graph between your defined limits. Now we're going to move on to what happens when the graph crosses over the x-axis. So when your graph goes below or above the x-axis, you'll split it into 2 parts. So here, for example, I've got a and b. So I'll work out the area of a by using a and b as a and 0, and then I'll use b, the area of b, I'll use 0 and b, and I'll work out the area for each. I'll modulate them, which means I'll make them positive. That's what those 2 lines there mean. And then I'll add them together, because that will give me the actual area. If they ask for the algebraic area, it means they want you to use the negative value if you get a negative value, but they won't ever ask for that, I don't think. So make sure you modulate the negative value. Just for anyone that's a bit confused, for modulation, if you've got negative 4 and you do the modulus of that, you'll get 4. And negative 8 gives you 8. Negative 15 gives you 15. There's a button on your calculator that does it. I think it's the absolute one. So if you push the button, it's top left, abs, and then you'll type 5 or probably negative 5. Push equal, it'll give you 5. I mean, you obviously don't need that button. I'm sure you're capable of getting rid of the negative sign, but that's how you do it if for some reason you weren't capable. Another thing you might get asked to do is work out the area between a curve and a line. Now the line or the curve on top, you call it y1, and you call the line on the bottom y2. Because you have to do it like this because you want to do the area under the first curve, the area under the curve at the top, take away the area under the curve at the bottom, so you're just left with the area between them. To get the area between them, you do your integration of y1 minus y2, and then you're going to sub in your value of b and then take away your total when you've subbed in your value of a. Remember, b is the one on the right, a is the one on the left. I went through that quite quickly, so I'm just going to run through it again. You do y1 minus y2, you integrate that, and then you sub in your value of b, write down what you get, sub in your value of a, write down what you get, and then do the one with the subbed in value of b, take away the one with the subbed in value of a. Make sure you get all your integration right, because that's the easy marks. core 1 stuff really. This is the trapezium rule, which is used to calculate the area under curves that are much harder to integrate. It's important to note that the trapezium rule will give you an underestimation of the total value of the area for curves that bend outwards, like the one in the diagram there, but an overestimation for curves that bend inwards. Sometimes that comes up as a 1 marker. If you're thinking in your head, oh my god, I can't work out what it is, draw your curve out and then draw your trapezium bits on and have a look and see, does it look like I've overestimated or underestimated, and you should be able to work it out. To do the trapezium rule, you split the area under the curve into lots of little trapeziums, which all have the same height, and height is when it's turned on its side, so it looks like width, but we call it height in the trapezium rule. It'll usually tell you what height to use, and will probably give you an indication of, it'll probably draw a table for you, to be honest, and put in some of the values, and you'll have to work out a few of the values of y for yourself. So for example, it might tell you that the height of the trapezium when x is -8 is 7, and then it might ask you to calculate the height when x is -6, and you'll literally sub in -6 into your function of the curve, like the curve. So y, say it was y equals 4x squared plus 3x minus 2, you would sub in -6 for all of your x's, and it would tell you the y value for x is -6. So the trapezium width at y0 is the width where it's a, which is -14, and the trapezium width at yn is the width at -4, so when you sub -4 into your function. It's quite advisable to draw out a table which will have all of your values of x and their associated values of y in, because that will really help you when you're putting all your numbers into the formula, because it's really easy to make mistakes if you don't do that. Then you've got to work out your height for each trapezium, and the height is b minus a, so the total length there between a and b, the total distance. So for us it's -4 minus -14, which is 10, so the height is 10. And then divide it by the number of trapeziums you've got. Here we've got 1, 2, 3, 4, 5 trapeziums, so you'll do 10 divided by 5, which gives you 2, so the height for this trapezium rule is 2, so you'll sub in h as 2. After that, it's simply a case of subbing in all of your values, so you'll have your value of y0 and yn, which is your y values when x is -14 and -4, and then 2 times all of the values in between added together. So that'll be 2 times the y value when x is -12, plus when it's -10, plus when it's -8, plus when it's -6. So if you write all this out on your paper and then plug it all into your calculator and then write out what your calculator tells you, obviously if it looks a bit unrealistic, then check it out. Also, if it gives you a negative number, then just make it positive, because the area has to be positive, but it might just give you a negative number because of the numbers you've put in. And do that for the other integration. Any integration you do where it's asked for an area, unless it's the algebraic area, give a positive area. You get this formula in the formula booklet, but make sure you've got grips with it beforehand, because it's quite tricky to use the first time. If you suddenly just see it and you're like, oh my god, this makes absolutely no sense to me. Just make sure you've done quite a bit of practice with it, and I will too, because I really need to do some more practice with it as well. And that is the end of the Core 2 revision video. Woohoo! Hopefully my voice didn't annoy you too much, and it's been a good revision process for you. If you need anything, then just comment below, and good luck in the exam. Have a lovely day. Bye.